Sorry for the delay. So before we get started, you should already finish the assignment 0. If at this point you are still doing assignment 0, which none of you seems does, you are in big trouble, okay? And so you really want to finish or wrap up stuff about assignment 1 by the end of this week, so you get enough time to deal with assignment 2, which is much more challenging than assignment 1. Assignment 1 is kind of just still warming you up. And about the line of code you need to write, assignment 1 is less than 100 lines. And assignment 2 is about 1,000 lines. Something like that. So you get the idea of the difficulty of the assignments. And today we're going to I'll quickly go over the things you need to do in assignment 1. And introduce some of the synchronization primitives you will need to implement, which is log, semaphore, condition variables, and rewrite log. And then if we have time, we can solve some synchronization problems. So in assignment 1, as in assignment 0, you have some code reading questions, and you need to implement several stuff. So for log, we have a log test. And so for CV, we have 2 tests, RW log, while matching problem, and intersection problem. So there are 6 tests you need to run before you submit the patch to make sure your implementation actually works. And the instruction also says that you need to write the RW log test by yourself to make sure your RW log works. But this part will not be graded. But it will help you to identify the problems in your RW log, but it will not be graded by the auto grader. So to do this assignment, you need to understand the concept of the critical section. So critical section is basically a piece of code. It has several properties. So first of all, this critical section must have access some shared resources, right? If one piece of code only accesses the resources that's private to you, it's not called critical section. So in critical section, you must have access to some shared resources. And this piece of code may not be concurrently accessed by more than 2 threads. So that's called exclusive access. So to help you understand the concept, let's use this printer example. So suppose we have a shared printer here connected by multiple clients. So we want to share this printer among these clients, there is a doPrint function provided by the printer to actually print the job you send to the printer. So our goal here is to design a wrapper function called selfprint to allow multiple users share the same printer, and also make sure the things print out don't mess up. Since we messed up if one job is printing and you send another printing job. So a first try without any synchronization will be like this. So in this selfprint function, we directly call doPrint. So obviously this solution won't work. Now why is that? Yeah. Yeah, exactly. That's the reason we want another wrapper of printing function instead of just doPrint, right? So the log is provided these semantics to enforce a mutual exclusion access to the shared resources. So in this case, the shared resource is this printer. And that piece of code is the doPrint function. So we want to make sure that only one thread can inside this function so that the printing can functional. And the log has several interfaces. These are two normal ones, like how to create a log and destroy a log. But the most important interface of the lock is these two, acquire and release. So we kind of already covered that in today's lecture. Lock acquire basically, if nobody is using the printer, you will using the printer and you will hold the lock. So if later on, before you finish the printing job, if another thread wants to also do print, he will get stuck in this lock acquire function. So lock acquire makes sure that only one thread can in that critical section. So when you're done, you can call this lock release to release the printer resource, so that if there is any thread is waiting for the resource, that thread can be waked up in the lock acquire and enter the critical section. And for this project, we also have a special interface called lock do I hold. Basically, it answers the question, so suppose a thread calls this function. It will answer, do you hold the lock? If the answer is yes, then we know that the caller of this function holds the lock. But if the function returns false or no, the caller doesn't know if this lock has been held by anybody else or nobody at all is holding the lock. So we don't have an interface called like is lock available, but we only have this one. So with the help of lock, our self-print function can be written like this. So we first acquire the lock. Before doing the actual printing, we first acquire the lock. So this line here is a critical section. Once you get here, you are guaranteed that nobody will enter this critical section before you leave this critical section. Right? So when you are done the printing, you release the lock and you continue. So other guys can come in and do the printing. So it depends on the behavior when the lock is not available. When you acquire the lock, lock has two kinds. One that you keep spinning there. It's called spinning lock. Another is called sleep lock. So the first kind of lock is, so when you acquire the lock and the lock is not available, a spin lock will keep asking if the lock is available. Are you available? Are you available? And keep asking that. So the pseudocode describing this will be like this one. So on acquire lock, we have a while loop here, keep asking if the lock is available. So line 2 is the actual spinning part. And once the lock is available, I set the holder to me, indicating that now I hold the lock, so I return. And the Spinlock release is quite simple. So we just set the holder to nobody, indicating I'm done with this lock. Anybody can continue and acquire the lock. Another kind of lock is sleep lock. It's more gentle. It's like, so when I come here, when I try to acquire the lock is not available. Instead of keep asking, keep bothering the lock if you are available, he just tell the lock, hey, I'm gonna sleep here. Wake me up when you are done, and I will yield the CPU to another thread to do some more useful job. So here's the pseudocode for the sleep version of the lock. As long as the lock is not available, I sleep here, because I know the previous holder of the lock will wake me up when he's done. So suppose the previous one done printing and call this lock release, we will first set the holder to nobody, indicating he is no longer holding the lock, and he will call this function called wake up someone. If someone is waiting for the lock, this function will wake the waiting thread from here. So after the waiting thread wake up, he will check if the lock is available. If it is yes, and we come here and set the holder to me and return. Now we say that second thread acquire the lock. So what's the difference between a spin lock and a sleep lock? So first of all, they are both locks. They support the same set of interfaces, which is lock acquire and lock release. So in terms of functionality, they are the same. But they do have some differences. That is the behavior of the spinning and the sleep. So for sleep lock, the good side of sleep lock is that when the lock is not available, instead of keep occupying the CPU, he just go to sleep. and yield the CPU to another thread. So there is no busy waiting here. But when a thread is going to sleep, another thread is going to run again, there will be a context switch. So the best side of the sleep lock is that the context switch overhead. Remember that in a context switch, we first need to trap into kernel. The kernel find another thread to run and bring it into memory and set it to be running. So all this takes some time. And for the Spinlock, the good side is there is no context switch. So I keep running. There is no context switch overhead. But the bad side is I'm actually wasting the CPU cycles when I keep spinning there. So the question is, when do we use a Spinlock and when do we use a normal sleep lock? So the trade-off is basically like this. Suppose the critical section is M CPU cycles, and the context switch overhead is N CPU cycles. When M is far less than N, meaning that the critical section is very, very short. So like, I just want to enter this critical section and modify a variable, and I'm done with this. So in this case, there is no need to go to sleep, because I know that whoever is already inside this critical section must have exit very quickly. So I just spinning for several times, and I will grab the lock. But in another case, when you enter the critical section and what you want to do is actually some very cost operations, like you want to perform some disk I/O. In this case, the critical section length may be very long, and far larger than the context switching overhead. So in this case, we favor the sleep version of the lock. Any questions so far? Yeah. Yes. Wait, what's our question? Yeah. You mean the wide channel lock function? Yeah. That lock? Inside the wide channel, the wide channel actually uses Spinlock if you go to the definition of that function. Right? Because when you write in wide channel, you don't actually have the sleep lock version working sleep lock. So the only lock you have is Spinlock. Yeah. And in OS 161, the Spinlock is already provided to you. So internally, the Spinlock uses this test and set automatic instruction. Here is the definition of the Spinlock. So we have a lock status variable called lock log, and to indicate if this lock is available or not. And we also have a holder information to tell you the current holder of the Spinlock. So note here, we use a pointer to the current CPU as a holder information. So in your sleep lock you will write, you may want to use some similar information to indicate if a thread holds a lock or not. So about this volatile keyword, basically in short, it told the compiler to do not optimize the code involve this variable. You can actually Google the volatile, see white space volatile to see more details about this keyword. So here is the function of the Spinlock acquire. First thing we do here is we disable the interrupt. So after this function call, we know that there will be no context switch on my CPU, right? So no threads on my CPU will compete with me with this Spinlock, for this Spinlock. And then we keep spinning here. This is the test and set function. So you can consider all this happen atomically. And so what does the test and set function do? Any thoughts? Yeah?
Will it check a value and then reset it with another value?
Did it check the value?
Yeah, it is checking that the lock is available or not. Lock
Yeah,
is available.
so the semantics of the test and set is this. First, set the value to 1. no matter the previous value is, and then return the previous value. So if you want to implement the test and set in C code, the first thing you do is save the previous value of the variable, and then assign the variable to be 1, and then return the previous value of the variable. So 3 lines of code. So initially, this lock is 0. What happens when the first thread acquires Spinlock? So it will disable the interrupts here and test and set this. Because the previous value of this log is 0, so it will set this variable to be 1 and return 0, right? And this expression says if 0 not 0, so it's false. We will come to here, line 9, we'll break. It means that at this point, I always grab the lock, so there is no point to be spinning anymore. I come here, I set the holder to me, and continues. And I say I already grabbed the lock. So before this thread release the lock, another thread comes in and also want to acquire the spin lock. What happens? So it first so the another thread must have been on another CPU, right? Because I have already disabled interrupts on my CPU. There is no context switch. I must be the threads keep running on this CPU. If there is any other threads trying to acquire the spin lock, that thread has to be on another other CPUs, right? So that thread, let's call thread B, disable the interrupt, and come here, try to test and set this variable. What happens? So now the variable's value is 1, right? Before it even do test and set. So this function will set the value to 1, meaning that this value doesn't change. But this function on thread B will return 1, because 1 is the previous value, right? 1 not equal to 0, this is true. We continue, come to here, and we test and set again, test and set again. This is this actual spinning part. Actually keep asking if this variable is 0, if this variable is 0, and so on. So the thread B will only pass this until the first thread A, set this variable to 0, right? If it is set to 0, then thread B will get a 0 and jump out this while loop. Yeah.
In the actual ASST1 code, there's also a if Spinlock data test and set right above test and set. So what's the difference?
Oh, this one. The comments actually explain that. So the hardware is to avoid a bus contention. So the hardware feature of the test and set register is that you need to have to read the value first before you can test and set. It doesn't have any relation of the overall logic of test and set. It's just some MIPS feature. You have to read first before you test and set. So I remove those 2 lines because in general we don't have those 2 lines. Yeah.
There's one question. Test and set is a machine operation, isn't it?
Yes.
So I mean, if we are making a sleep thread, not sleep lock, not spin lock. If you're making our whole implementation of sleep lock, so how we will call this machine code?
You don't.
Oh.
Yeah, you in your sleep lock, you don't use the test and set.
Okay.
I just want to explain how the spin lock works because we covered that in the lecture, right?
Okay.
Yeah. So everybody now get how the spin lock works. Okay, so spin lock release is quite easy. We just set the holder to nobody and set the lock variable to 0, indicating that the lock is now available again. So, and we re-enable the interrupts and we continue. So, the questions. In a single core case, does the spinning part necessary? Do we really need to spin in a single call? Yes or no? No, why? Because of what? Yes, because we have disabled interrupt. There will be no context switch. Whoever grabbed the log must have keep running unless he re-enable the interrupts, right? But in the multi-core case, this spinning part is necessary because you can only disable the interrupts of your CPU core. If another thread is running on another CPU core, you cannot disable it, right? But the other threads will get stuck here. So either in single core case or multi-core case, we already have a way to prevent another thread to enter the critical section, right? And for a sleep version of log, which you need to implement, is not provided. So when you design this version of log, you want to be able to answer these questions. So how do you tell whether a log is available or not? Any thoughts? Yeah. Log do I? No. I mean, yeah, log do I hold is a function you provided to the outside world. Internally, how do you decide if a log is available or not? Who is holding the log? Yeah, that's one way. So in the previous Spinlock case, how does Spinlock how do we tell if the log is available or not? We have a special variable. If this variable is 0, then this log is available. If it's not, then log is not available. So these questions you need to answer when you actually decide which to put in the log structure, right? You need, somewhere in the log structure, you have to maintain a state of the log, if it's available or not. And this state is shared by multiple threads, right? Whenever you have a variable that shared multiple threads, and the next question will be, how do you synchronize the access of this log state? Yes, spin logs. Because we already have provided the spin log to you, right? And in the semaphore implementation, we also have the same issue. Semaphore have a state. And how do we synchronize the access of the semaphore state with the spin log, right? Here the same thing. And how do you answer the question, log do I hold? So it's not sufficient to tell if a log is available or not, but you also need to answer, do I hold the log? Right? So you need to store some kind of holder information on the log, so you can do check if the holder is me or not. Right? And where should the thread sleep on when the log is not available? Where channel? It is easy, right? That's the only mechanism on OS 161 where you can sleep. And so in the previous case, we only have one printers. So we use log to synchronize the access of the printer. Now, suppose we have more than one printers, will this simple version of using log, will this work?
You can use semaphore to multiple.
Yes, exactly. So it will still ensure mutual exclusion, meaning that since will be not messed up, it will still making some progress. Everybody eventually will get it to print, but the performance will be bad because we have multiple printers, and the log only allows one users to printing stuff. So here's where the semaphore come into play. And semaphore is used to manage a set of shared resources, and it allows up to a certain number of threads in the critical section at the same time. This number depends on how many resources you have. So semaphore's interface, the normal interface like create and destroy, and P and V, as explained in today's lecture. P means try to decrease the counter, and V means try to increase the counter. So with the help of the semaphore and P and V, we can write our self-print as this. So initially, there are 5 printers, So I initiate the semaphore count to be 5. And everybody just P this semaphore before do the actual printing, and V the semaphore after the printing is done. So this will allow up to 5 threads in this critical section. So what's the difference is between the lock and semaphore? We kind of already covered that in the lecture. So lock only permits one thread in the critical section, but semaphore can permit multiple threads. Lock has a holder concept. We can say who holds the lock, which thread holds the lock. But for semaphore, we don't have such a concept. There is no such thing that who holds a semaphore, because the semaphore represents a set, a group of resources, right? We cannot say which thread holds the whole resources. So lock is more or less like a binary semaphore. And semaphore is already provided, so you want to make sure you understand how semaphore works, the P and the V, before you implement your lock. Here's the definition of the semaphore structure. So let's see how the designer of this semaphore answers the questions. So how do you tell whether a semaphore is available or not?
Counter.
We have a semaphore state, that is the counter, right? If the counter is positive, we know the semaphore is available. If it's 0, we know there's no resources available. And how do you synchronize the access to semaphore state? We have a Spinlock. So whenever we access the semaphore count, we always protect it with using this Spinlock. And yeah, the thread should sleep on this web channel when the semaphore is not available. So your lock structure should have more or less the same things, except that you need to add one more field, the holder information. Here is the P function of semaphore. So we first acquire the Spinlock because we're going to take a look at the shared state, the sem count. As long as the sem count is 0, so let's just suppose I'm the first thread here. I'm the first thread called P function. This sem count will be positive, right? So this is false. I directly come to here and minus the count by 1 and release the Spinlock. I'm done. I already acquired 1 resources. And the second thread comes, the semaphore count is still positive, and keep going. So suppose we have 5 printers, up to 5 threads can go through the process and acquire a resource. Now the 6th thread comes. So the semaphore count is 0. What happens? It has to wait, right? So he lock on this wait channel, and at this point there is no meaning of still holding the Spinlock because the counter is 0. We need to give up the Spinlock so that somebody else can actually increment the sem count. And we sleep on this web channel. And when we wake up, we know that the resource must have be available again because somebody have already woken me up. So I require a Spinlock and go back to check if the count is positive. So those 4 lines here are the critical sections protected by this Spinlock. Yeah. This one? So think this as this way. Inside the W chain lock, actually it just do one thing. Lock the Spinlock of W chain. W chain has a Spinlock. So what it does is, so when multiple threads want to sleep on the web channel, you can consider as a linked list or queue, right? This is a shared data structure. Multiple threads want to sleep on this web channel. So before you can, if you want to sleep on this web channel, you have to add yourself to the tail of the web channel, right? That will be modifying the shared state. So this web chain lock is just to, I first lock the web channel, so I know that I hold the lock. Nobody can append themselves to the tail of the web channel before I release the lock. So this is to protect the web channel. Actually, that's a good question. So What's the critical section protected by the web channel lock?
Adding when you are adding new ideas should hold the lock.
Yes.
Till you
So
add
the first line acquire the web channel lock, and line 5 and 6 and are actually on the critical section of the web channel lock. So inside the web channel sleep, it will first add this thread to the web channel, and then release the web channel lock. And then, yes, so this is the critical section of this web channel. Any other questions? Okay. So in the V function, it's much simpler. We just acquire the Spinlock, increment the counter to return the resources you acquired, and wake up somebody that's potentially waiting for this resource in the web channel. Right? So before we continue talking about the condition variables, and I want you to make sure you can answer these questions. So why do we need logs? Because we want to enforce exclusive access to shared resources. And what's a lock interface? Basically two: acquire a lock and release a lock. The difference between Spinlock and sleep lock is the behavior of when the lock is not available. So which lock to use in different conditions? Basically the trade-off of this critical section length and the context switch overhead. The Spinlock, so OS 161 internally use test and set instruction to implement Spinlock. For semaphones, why do we need semaphones? Because we have multiple resources we want to manage. And a semaphore interface is P and V, try to decrease the counter and try to increase the counter. And how the OS 161 implement semaphones. Use Spinlock to synchronize the state of the semaphore. Okay? So condition variables. So actually, the difficult part is not to implement the condition variables. The implementation is quite easy. The difficult part is to try to understand how condition variable works, how the user uses the condition variable. So I will demonstrate how the usage of a condition variable in the later slides by example. So it actually lets the threads to temporarily give up the exclusive access to wait for a certain condition. And when that condition happens, after this thread waking up, regain the exclusive access and resuming the task. This sentence will make much more sense once we get to the example part. So the interfaces, we have a CV wait. Note that in CV wait, we passed in a lock variable. So we first release the supplied lock. This indicates what? So whoever called this CV wait function must have already have the lock. Right? Otherwise, this doesn't make sense. Right? And the second step is once we release the lock, we go to sleep by call wait chain sleep, and then after waking up, reacquire the lock. So the CV wait actually doesn't change the state of the holder of the lock. So before CV wait, the caller should hold the lock. After CV wait, you should still hold the lock, right? Except that inside it, the CV wait actually first release the lock for you and then acquire the lock for you. But an overall effect is that the CV wait doesn't change the lock status. We have a CV signal and a CV broadcast to wake up somebody on the web channels. So here is the producer and consumer problem example. So suppose we have one bounded buffer with certain maximum capacity. And there are two kinds of threads. One is producer. All it does is to produce some data and try to put to this buffer. Another type of thread is consumer. So all the consumer does is to get some data from the buffer and consume it. So here is the producer code. Let's take it one line by line. First, we produce some item, and then we acquire the buffer lock. Because the buffer is a shared resource, between the producer and the consumer, so we have a lock to protect it. So we first acquire the lock. As long as the buffer size is full, is max, meaning that this buffer is full, I wait on this CV with this buffer lock. So suppose now the buffer is full. What happens? The producer waits here, right? Inside the CV wait, the CV wait will first release this buffer lock and then go to sleep. And after waking up, we acquire the buffer lock. So if we return from the CV wait and come here, we still hold the lock. Right? It assures that whenever we access the status of the buffer, we already hold the lock because this is the critical section. And then suppose now the buffer is not full and we add the item we just produced to the buffer and signal somebody. Here is the code for the consumer. So the consumer wants to get some data from the buffer. So he first acquires the log from acquire the log and see and check if the buffer is empty. If it's empty, we call CV wait on this condition variable and sleep there. And after wake up, we check the buffer size. So now the CV actually, the condition variable actually enables this rate. So at this point, as line 4, this producer holds the lock, right? But the buffer now is full. If you don't give up the lock, I mean, if you go to sleep without release the lock, can this consumer actually consume some item from the buffer and then make the buffer not full? No, right? So we require that this producer temporarily give up the exclusive access to the buffer so that other consumer threads can change the buffer status from full to not full. And same thing here. So when the buffer is empty, the consumer has to give up this buffer lock temporarily so that potential producers can produce item to this buffer and then make the buffer not empty. And also note that we have both CV signal both in producer and consumer. Because when the producer successfully puts an item on the buffer, the producer doesn't know if there is any consumer waiting on the wait channel. So just a CV signal it in case somebody is waiting. If nobody is waiting, the CV signal has no effect. Same thing here. So when the consumer consumes the item from the buffer, it signals potential waiting producers. Any questions? Everybody got it? Yes.
When a consumer signals a producer.
What's the question?
When a consumer signals a producer.
Consumer. Oh, yeah. So suppose the initial state of the buffer is full. Now the producer wants to produce an item to the buffer. The producer has to wait, right?
Yeah,
CV wait here.
How does the producer know who a consumer is?
The producer doesn't have to know, right? The producer just wait here, wait until the buffer is not full, so I can put an item on it. And later on, another consumer comes and consumes the item from this buffer. Now the buffer is not full, it has one more available position. So he does CV signal to signal potential producers, hey, you can keep producing. There is a slot available, right? You?
In CV we are temporarily releasing the lock.
Yes.
And then regaining it.
Yes.
So there is no guarantee when we will get the lock again. In the between.
There is no guarantee, but as long as you call lock acquire, you will eventually get the lock.
You can get after some time also.
Yeah, eventually you will get it.
Eventually.
Yes.
So I was just asking that if should we raise the interrupt level in CV wait or no?
No.
Just because other can get it.
Yes. So for reader and write log, it just basically want to differentiate the rules of reader's race and writer's race. So the idea is multiple readers can in the critical section without causing any conflict. But only one writer can in the critical section. So when you implement the RW lock, you want to enforce the semantics. So you want to enable multiple readers to enter the critical section at the same time. But at the same time, you want to make sure that once a writer is in the critical section, there will be no readers and writers in that critical section. And also, you don't want to starve the writer, because so suppose the thread arriving sequence is like this. First, we have a couple of readers coming. The first reader comes, nobody is in the critical section, so the reader comes in. The second reader comes in, fourth reader comes in. Now we have a writer comes. So the writer see, oh, there are some readers in the critical section. I better be wait here until the readers vacuum the critical section. But as the writer is waiting, more readers coming. Now, the readers see that only readers are in the critical section, so I'm free to come in, right? So the readers keep coming and keep coming. This writer got stopped here. So you want to avoid this case. You can use whatever synchronization primitives you like, and you don't want to use spin locks. Once you have the normal locks, you just get away with spin locks. Are we done with running out of the time? Oh, okay. So while making, well, let me just quite quickly cover this in less than 2 minutes. Okay. So these problems, we have two kinds of whales, males and females, and so these are from the instructions of the website. So this actually tells you exactly what male and female should do. And so you want to wear them properly. For the stoplight or intersection problem, you want to first ensure safety, meaning that no two cars in the same quadrants at the same time. And then efficiency means that you do not want to use a whole big lock to protect the intersection. And deadlock, you don't want to a car come here, turn left, and the car come from here, turn left, get stuck here. So you want to avoid a deadlock condition. That's pretty much it for today. Well, let's